Swayam Prabha. Digital India. Educated India.
Welcome to lecture on flow of water through soils part 1. After having covered the concept of effective stress in saturated soils and partially saturated soils and effect of fluctuations of water table on effective stress and capillarity phenomena, we will be now discussing what will happen when water flows through soils, how water can flow through soil and how important it is in the consideration of soil mechanics engineering. So, in the previous lecture, we have understood about this effective stress concept and we have discussed in length about total stress is equal to effective stress plus pore water pressure. Then we also discussed about the condition for partially saturated soils. Then in case of fluctuations of water table under no flow conditions, we have discussed that what are the consequences of fluctuations of water table on the effective stress, and finally we discussed about the capillarity phenomenon. So, in this lecture, in the beginning of this lecture, let us again look into the concept, particularly the practical examples pertaining to capillarity phenomenon. So, as we discussed in the previous lecture, we said that there will be different types of waters in soil. The water table which is that is called groundwater table, which is this particular region and which represents the groundwater regime, and here the capillarity zone or a capillarity water which can occur and which can keep the soil under saturated conditions. This depends upon the type of the soil. And another one is the gravitational water. This is basically an intermediate zone which comes under the Wados zone, and then soil water. So, what we have seen is that there is a zone of aeration. So, that means that there exists a partially saturated soil and there exists a zone of saturation that can occur below the groundwater table. So, while looking into the physical examples of capillarity phenomenon, we have introduced two examples in the previous lecture. Now, we are just looking into them once again. So, here consider in this slide along the beach, we always come across the soil which is in certain region has got certain good strength or carrying capacity which can encourage movement of the vehicles, or which can also have one can walk easily on that particular type of soil. When you go away from that certain zone, you will find again the soil of poor strength, and towards the zone where water breaks, you will find again the soil of poor strength. The reasons could be entirely due to this capillarity phenomenon. So, here in this zone where soil exhibits good strength, that is exhibiting because of the confining pressure results from the column of water hanging on the different menisci at the surface of the beach. So, when this is remain in this condition, the hanging water columns which are there in this pore spaces will try to have something called a negative pore water pressure, which influences something called an increase in the effective stress. That results in the soil of good strength, where if you consider the relative density is more or less same in the entire location. So, though the relative density is more or less same, only change in the presence of the capillary moisture and its absence. Because of this, it exhibits this particular phenomenon. Particularly in this zone, when the seawater breaks, capillary menisci gets washed off and temporarily induced shear strength is lost. So, because of this negative pore water pressure, this can overcome once this wave, once the wave breaks, then what will happen is that these menisci, which are these hanging water columns which are there in the pore spaces of the soil, can get washed off. In the process, when the soil becomes again saturated, then it loses all the strength. So, this is one certain example where a capillarity phenomenon exists. The another example is we discuss particularly in case of moist sand under partially moist sand under the moist conditions, that is a partially saturated sands. For example, when you have got a sand with partially saturated conditions, you will see that there is a capillary water formed by the soil particles. That means that there will be a thin film of water which is surrounding these grain particles, and which in turn, because of the surface tension force, what will happen is that this the force in the menisci, that is the surface tension, because of the surface tension, which actually exerts a compressive force at grain to grain contacts. In the process, it actually resembles something like an enhancement in the increase in the shear strength because of the more friction. So, this results something called a bulking structure in sand due to capillary action. So, partially what is happening here is that the strength gain in granular soil due to partial saturation and surface tension is termed as capillary, it is termed as an apparent cohesion. Surface strength gain in granular soil, strength gain in granular soil due to partial saturation and surface tension is termed as apparent cohesion. This apparent cohesion is very significant under partially saturated conditions, but once this when it is subjected to saturation, what will happen is that this particularly this strength gain whatever we have got during the partial saturation, we can get rid of that, then there will be this apparent cohesion disappears. So, that is why this particular name which is appeared, which is given for this cohesion is called apparent cohesion. So, let us define once again the strength gain in granular soil due to partial saturation and surface tension is termed as an apparent cohesion. So, why we are required to study flow of water through soil? The motivation, let us try to look into this slide. The ability of engineers to understand and predict the flow of fluids, usually water in soils, is essential for many applications in civil engineering. So, having seen the application, particularly practical examples relevant to capillarity phenomenon and effective stress conditions under no flow conditions, now we will be trying to understand what will happen when the water flows through the soil. What is the motivation behind this study? Let us look into it. So, consider it has got importance from environmental engineering or construction engineering point of view, or dealing with certain construction activities in soil. So, definitely this particularly the flow of water through soil or a fluid flow through soil is very important and very significant. So, consider here in this slide holding lagoon where a toxic liquid is stored. So, the questions always will come is that whether we can retain this particularly this toxic liquid in place or not, or at what rate is toxic liquid escaping the holding lagoon. So, in case if you are not able to retain with a proper method, at what rate it disappears, it starts escaping the holding lagoon, and how long might it take the liquid to reach the groundwater table. So, the rate at which it can flow through the liquid, that is again needs an understanding about flow of water through soils, and what can be done to slow down the rate of the escape from the pollutants. Is there any possibility of constructing barriers? That is the question which is required to be answered. This can be done once we understand this particular study or a chapter on flow of water through soils. In terms of the construction engineering, generally for bridge pier construction in rivers or so, a coffer dams which are constructed and for that a sheet pile walls, basically this type of structures are driven into the ground, and water was retained on the upstream side, and the construction activity is carried out temporarily. So, here the safety, particularly what will happen is that when there is water is retained, the water tends to move or flow in this direction. So, in the possibility whether is there any instability due to flow of water in this particular location or not. So, this is required to be understood from the construction engineering point of view. So, the questions which are required to be answered in the previous slide for the construction engineering point of view, they are: what will be the rate of water flow, water inflow into the site? That means that the site is referred here is the one which is in between the space which is formed within the cofferdam structure. Is it possible that soil will liquefy and endanger construction workers? That means that liquefaction is nothing but a momentary loss of shear strength because of the upward flow of water. So, is it possible that the soil will liquefy and endanger construction workers? So, our objective here is to gain an understanding of the mechanics of fluid flow in soils, so that engineering problems of this type can be eventually addressed. So, this type of engineering problems like what we have seen, for example, holding lagoon or a construction of a cofferdam structure, this can be answered once we understood the mechanics of fluid flow in soil, so that engineering problems of this type can be eventually be addressed. So, now having introduced, now let us look into again soil, which is nothing but assemblies of particles. So, when water flow can flow in any direction, it can take any path. So, the path taken by the water is along the pore spaces, within the soil mass. That means that if you treat the soils or assemblies of solid particles. So, this is a solid particle and this is a solid particle, and what this is a particular flow path, water can take a flow direction like this. So, this can flow once it is subjected to some higher energy here and lower energy here, like current it flows from high potential to low potential. Similarly, here the water tries to flow from higher energy to lower energy. So, it can have innumerable number of flow directions or flow paths can be established. The flow of water path, particularly water path within the soil particles, is called tortuous path. So, soils are assemblies of solid particles with interconnected voids through which water can flow from a point of high energy to a point of low energy. So, this particularly in order for the flow to take place to the soil, it should have something called a high energy at an upstream point to the low energy from the at the downstream point. If that is exists, then there is a flow which can take place. For example, if there is no difference in energy, then what will happen is that it indicates that the flow is not taking place. So, it represents when the flow, when there are no flow conditions, it is called something called hydrostatic condition, that we are aware from the previous lectures. So, basically the study of flow of water through porous soil media is important, because if you look into this particular number 0.1 involving the rate at which water flows through soil. That means that determination of the rate of leakage through an earth dam. For example, if you have got an earth dam, the interest is that the rate of leakage of an earth dam. So, that is very much important to assess and to know in the design of earth dams. So, involving the rate at which water flows through the soil. So, sometimes it dictates now for us to even select materials based on this particular criteria. When we wanted to have rapid water flow, then particularly for say parking lots where you wanted to provide a drainage medium, then you need to have particularly a medium or a soil at which water can flow rapidly. Where you wanted to say prevent migration of water, then in that case you are required to have a material which can stop. Particularly this type of questions can be answered by varying the type of soil and involving the rate of settlement of a foundation. That means that if you are constructing and if the soil is undergoing consolidation, at what settlement rates, at what rate the settlements will occur, and what rate the loads will transfer, and what rate this effective stress transfer will occur in soils. In that, if you wanted to understand, means the knowledge of fluid flow through soils is required. and involving the strength, that is the evaluation of the factor of safety of an embankment. So, whether it is a long term parameters, something like long term strength or short term strength, depending upon the type of the structure under consideration in involving the strength of a soil, that also depends upon the amount of water which is flowing out of the soil. So, this indicates that the study of the flow of water through porous media is very important. Now, let us consider in this slide, which is shown an assemblage of solid particles. So, the voids which are in between, the blue ones what you are seeing, assume that they are occupied by water. Now, A is a point and B is a point. A, let us assume that having a higher energy, and B is a point we having low energy. So, the flow can take place from A to B, and this is the direction of the flow. Now, if in reality the flow path of a water which generally looks like this, which is a winding path or which is defined as a tortuous path, that is along the contact points or along the pore spaces of the soil medium. But like we did in effective stress, what we do is that we look into macroscopic point of view and take a line passing through solids as well as pore spaces and contact points. So, that is defined as a flow path under macroscopic scale. So, the water does not flow from point A to B in a straight line, but at constant velocity, but rather in a winding path from pore to pore, and depending upon the size of the pore, its velocity within the pore also changes. So, here at A it has got higher energy and B which has got a lower energy. So, water, it enables water to flow from A to B. So, what we seen is that here in this case the water, when it is flowing through the soil particles, it will have is something called a winding path, or which is defined as a tortuous path. But in reality, if you consider that A to B, it is not actually not flowing in a straight line from A to B, but it is taking a path which is called a winding path or a tortuous path. Now, let us look into the Bernoulli's theory of application of fluid mechanics here. According to Bernoulli's equation, we knew that the total head is equal to pressure head plus velocity head plus elevation head. So, here according to Bernoulli's equation, the total head at a point in water under motion can be given by the sum of the pressure, velocity and elevation heads. So, Pw by gamma w represents the pressure head of the fluid and has the unit of length. So, H is equal to Pw by gamma w, P is the pressure, gamma w is the unit weight of water, V is the velocity of flow through the soil, and G is acceleration due to gravity, Z is the elevation in meters. So, if you look into this, the total head is a summation of Pw by gamma w, that is pressure head, plus velocity head, which is nothing but V square by 2Z plus Z. Z is nothing but elevation head with reference to a particular or a selected arbitrary data. Now, what will happen is that in case of soils, when the water is flowing through soil, the velocity is so small, the V square by 2Z term is very, very small. So, what we generally consider in soil mechanics, which is different from fluid mechanics, is that total head is equal to pressure head plus elevation head. So, V square by 2Z represents the kinetic or velocity head of the fluid and also has units of length. Since water flowing in typically has very small velocities, the velocity head is typically negligible compared to that of the pressure head and elevation heads. So, for this reason, velocity head is neglected in soil mechanics. So, this total head, in the sense what we do is that we write something like pressure head plus elevation head. Z is the elevation with reference to an arbitrary datum. So, the value is the distance of the point at which the head is being measured above the datum. So, this particular head measurement whenever we are taking, so the point from where selected datum to a point where this head is being measured, that is referred as a elevation. So, this can either be positive if the point is above datum, negative if it is below datum. So, the sign convention what we follow is positive if it is above datum, negative if it is below datum. So, in soil mechanics, the total head is defined as pressure head plus elevation head. So, with the deliberation whatever we have discussed now, and we found out that the flow of water through soil is very significant and has got lot of potential and importance in soil mechanics. Now, let us look into the concept and mechanism what happens when the soil when water flows through soil. So, water flows in soils only when there is a gradient of head h. That means that there should be a certain energy, so that water can use that energy and it can flow through soils. So, lack of gradient in head implies that water is not flowing. That means that if the head which is available for the flow is say less or it is not inadequate, then it indicates that there is no flow taking place. Whenever there is a water flow in soils, there is energy dissipation occurs. So, for the flow to take place, it has to spend the energy. That means that whatever the energy it has got to enable the flow to take place, so that energy dissipation occurs. So, at the beginning when this water is entering the soil phase, it can have a full energy. By the time it comes out of the soil path, then it loses all the energy. That means that when the flow takes place through the soil, a certain sort of energy dissipation occurs. In soils, water are permeant. If the fluid which is different from water, then in that case it is called permeant. The one which flows through the soils is permeant. Always flow down the gradient. That does not necessarily that you need to have down the hill. If even under confined conditions are so, if there is a difference in head, even in the upward direction also water can flow. If the head, that means that if there is a energy from point 1 which is lying at the lower level to point 2 which is lying at the upper level, it can flow with by virtue of an energy. So, this that is the water flow from higher energy region to low energy region. That means that water flows from higher energy regions to lower energy regions. So, flow of water through soils which is linked with this particular legend here which is shown, water flow in soils, that means that energy dissipation takes place. Even for water flow in soils to take place, gradient in head h is required. So, if there is a gradient in head h, then water flows in soils and then energy dissipation occurs. So, this we have understood that the flow of water through soils, it can take place provided if there is the higher energy or a higher head at upstream end, or a point 1 where the energy is high, and a point 2 for example where the energy is low, then the flow can take place from 1 to 2. When the water flows from 1 to 2, in the process it undergoes something called an energy dissipation process. So, let us consider a uniform head distribution in a soil deposit. So, in this slide example 1 where the groundwater table is shown here at 2 points here 1 and 2 where the pressure head is H1, elevation head is Z1. So, this is the datum here. So, total head is H1 plus Z1. In case of this particularly this point 2, the elevation head is Z2, that is very close to the datum, and H2 is the pressure head. So, H2 plus Z2 is again total head H. Now, if you look into it, here the total head at H, total head at point 1 is H and total head at point 2 is again H. So, as the total head H is identical, flow will not take place from 1 to 2. So, this type of condition we define as hydrostatic condition. So, we have used the previous lectures, all we have determination of effective stresses. What we consider is that the groundwater table which is hydrostatic in nature. So, in this slide what we have seen is that uniform head distribution in a soil deposit. So, as the total head H is identical, flow will not take place either from 1 to 2 or 2 to 1. Let us consider in case of head in static water in capillary tube. Previous lecture we saw that above the water table the columns, hanging water columns, that is the columns which are passing through pore spaces sucks the water from the water table and keeps in it. That by virtue of a phenomenon called surface tension, which is acting along air, water and inner surface of the solid grains. So, this is Hc. We have discussed and seen that as a capillary height, and one is that meniscus. So, let us consider 2 points 1 and 2. So, this is that Hc which is the above datum, that is above groundwater table level. At groundwater table, that is point 2 is at atmospheric pressure, where pressure is equal to 0. So, water rising above that, which is less than atmospheric pressure, is negative. So, if you consider at location 1, say elevation head is Hc meters above datum, this plane is selected as datum. Pressure head is minus Hc, that is by virtue of the definition just now we have given. So, total head is equal to elevation head plus pressure head, total head is again 0. So, 2 that is this point at datum, elevation head is 0, pressure head is 0. So, in the process total head is equal to 0. So, here there is no flow of water in this particular situation. This is this capillarity phenomenon is just because of the surface tension which is arising at air, water and inner surface of the solid grains. So, this also demonstrates that if there is no head difference, then the flow will not take place. Now, let us consider an example 3. So, this is what we have seen, the fluid at rest in soil, no flow conditions. So, even the capillarity phenomenon what we have seen appeared like flow, but it is something called a no flow condition. So, here that is one which we have discussed, is that pressure in water is less than atmospheric pressure, that is negative in the capillary zone. That is the reason why the pressure head which is taken as minus Hc, and here is that moist dry soil, and here below the groundwater table again the positive pore water pressure exists. So, this is that the zone of capillary saturation. If there is a partial saturation exists, then this negative pore water pressure tends to fall and then reaches 0, and ultimately the pore water pressure is 0 in this particular zone. If it is dry because of the climatic fluctuations, then it can change to 0 there. So, this is actually a condition which what we discuss is the fluid at rest in soil, no flow condition. Now, let us consider flow of water through soils under confined aquifer, through a confined aquifer. So, assume that here at point 1 at an elevation Z1. So, this is the reference datum here, Z1 which is the elevation head, and pressure head here is P1 by gamma W. So, at point 1 the total head is nothing but P1 by gamma W plus Z1. If you come to point 2, the pressure head is P2 by gamma W plus Z2 is the elevation above the datum. So, total head at point 2 is P2 by gamma W plus Z2, that is H2. If you observe that H1 is greater than H2, then water flows down the hydraulic gradient from point 1 towards the point 2. So, this is this particular, if this is the length L, then over this length L, then the loss of energy is occurring at this rate. So, if you see here H1 and H2, that is the total head, the difference between H1 and H2 between 2 points, which is referred as head loss, that is delta H is nothing but H1 minus H2. So, for the flow to take place, down the hydraulic gradient, not necessary that downhill conditions should exist. Naturally, when there is a downhill conditions are there, the flow can take place from higher level to lower level, but it's not necessary that it should prevail always. If these conditions exist, then water can flow like this from 1 to 2 if there is a head at point 1 is greater than point 2. That is, when H1 is greater than H2 with a loss delta H, the water can flow with a certain gradient. So, when looking into the flow of water through soils, and we assumed that water flow takes place in a microscopic point of view along a tortuous path through pore spaces, and so there are some assumptions, and then the theory which comes out is Darcy's theory. But basically these assumptions are involved are soil is fully saturated. So, this soil is fully saturated and frictionless boundaries, assuming that when the flow to take place, the boundaries which are free from any friction, and flow is laminar. That means that the Reynolds number, particularly in case of soils, it is defined as rho v d10 by mu, where the rho is the mass density and v is the velocity of flow, which is called the discharge velocity, and d10 is the effective particle size, and mu is the dynamic viscosity of water or premiant under consideration. So, when the assumptions involved are flow to be laminar, that is Reynolds number has to be less than 1. In fluid mechanics, we use around 2000 for defining the laminar conditions, but in soil mechanics, which is different, which is here indicated as Re less than 1, the flow to take place through soils under laminar regime conditions. Now, consider a saturated soil mass confined in a cylinder having a length L, and assuming that these boundaries are frictionless, and which is this point 1 and point 2 or point A and point B subjected to a head, total head is HA with PA by gamma W and a ZA elevation head. So, total head is equal to HA, and total head at point B is equal to PB by gamma W plus ZB, that is HB. So, the head loss occurring between A and B, that is HA minus HB, the head loss occurring between 2 points A and B, it is HA minus HB. So, here this is the cross sectional area A, which is perpendicular to the direction of the flow, So, in order to maintain these two total heads, what happens is that a constant source of water has been supplied, any extra level of water is collected in another jar. So, here this particular head is maintained. So, what exactly, if you measure this particular discharge here, that is nothing but the one which is flowing through the soil. So, this is the cross sectional area A, which is exposed to the water to flow through the soil, and delta H is nothing but HA minus HB, the difference where HA is greater than HB. So, the head loss between 2 points, which is nothing but delta H is equal to HA minus HB, which is nothing but PA by gamma W plus ZA minus PB by gamma W plus ZB. The head loss delta H can be expressed in a non-dimensional form in terms of a parameter called hydraulic gradient I, which is indicated by I is equal to delta H by L, where delta H is nothing but a head loss, that is the difference of total head at point A and point B, and L is the length of the flow over which the loss of head occurred. That means, this is the one which is something like in a macroscopic point of view, a straight line passing through pore spaces as well as solids, which is an imaginary line which is taken as the flow path. So, I is equal to delta H by L, very important parameter in pertaining to flow of water through soils is hydraulic gradient, which is defined as delta H by L. So, when the water flows through soil, it exhibits V has got certain relationship with I. So, I which is plotted on x axis and V which is on y axis, V is nothing but is called as a discharge velocity or superficial velocity, because it is called superficial because it is the one water which flow which is taking place through the soil as well as soil solids as well as through water in the pore spaces. But in principle, the flow velocity of flow through the grains or through the solid grains is different. So, that is the one definition which we are going to look into it shortly, but if you look into it, if the hydraulic gradient increases gradually, the flow remains laminar, that means that V is proportional to I, whatever V tries to proportional to be I, and it remains in laminar regime. And after certain when the hydraulic gradient increases, it transforms into zone 2, which is called as a transient zone. Above that zone, zone 2, it is zone 3, which is called turbulent zone. So, when I increases gradually, the flow remains in laminar zone in zone 1 and zone 2, and V bears a linear relationship with I. So, both in zone 1 and zone 2, V bears a linear relationship with I. At higher hydraulic gradients, that is higher values of I, flow becomes turbulent. So, in most of the soils, V is proportional to I. In gravels and very coarse sands, the V is proportional, to be proportional to I is not valid. That means that in most soils, V is proportional to I, that means the laminar regime exists. In gravel and very coarse sands, turbulent flow conditions may exist and V is proportional to I is not valid. So, the flow of water through gravelly soils also a certain type of the regime which takes place is the turbulent regime, where the Reynolds number is no longer less than 1. So, by looking into this relationship between velocity, which is nothing but discharge velocity or superficial velocity, and hydraulic gradient, Darcy has proposed an equation based on proportionality between discharge velocity and hydraulic gradient. After Darcy 1856, this is known, a simple equation for the relating the discharge velocity of water through soil, through saturated soils. Basically, the assumption is that saturated soils, and which may be expressed as V is equal to K I. V is the discharge velocity or superficial velocity, I is the hydraulic gradient, and K, which is defined as coefficient of permeability, very important parameter pertaining to flow of water through soils. So, K is also called Darcy's coefficient of permeability. The units of coefficient of permeability are equivalent to the velocity, that is meter per seconds in SI units. So, V here, that is the discharge velocity or superficial velocity, which is the quantity of water flowing in unit volume through a unit cross section of soil at right angles to the direction of flow. So, V is nothing but discharge velocity or superficial velocity, which is the quantity of water flowing in unit volume through a unit cross section of soil at right angles to the direction of flow. So, flow is through the pore space in soil, not through the entire cross section area. So, if you look into it, the flow which is taking place is through the pore spaces which are available in between the solid grains, not through the entire cross section area. That is the reason why this particular velocity, which is indicated in this Darcy's equation V is equal to K I, is called discharge velocity or superficial velocity, or some extent it is given name called fictitious velocity. So, this particular Darcy's theory or V is equal to K I equation is formulated based on the observation of flow of water through clean sands. In an ideal condition, a clean saturated sands. So, flow of water through clean saturated sands.